Okay, welcome back to chapter 2. We're in section 2.7 now. And we're going to look at atomic mass. So this is the mass of an element in atomic mass units, or AMUs. Oops. I went backwards, so hold on a sec. I went backwards quite a bit. All right. Okay, so AMUs. And the atomic mass unit is by definition equal to exactly 1/12 the mass of a carbon-12 isotope. Now, atomic mass we're going to find on the periodic table. For example, we might have element number 1, which is hydrogen, and it might have the value of 1.0079. And so this is in AMUs, and this is an average atomic mass. It's called a weighted average. And we're going to look at what a weighted average is. And it has to deal with how many isotopes a particular element has. And for those isotopes, what is their percent abundance in nature? So it says an element has 4 naturally occurring isotopes. And so given the following data, it says that here are the masses in AMUs of the 4 isotopes and their percent abundances. So if we were to walk down the street and the heaviest isotope here, we would meet 52.3% of the time. So 52.3% of the overall mass of the average of these 4 isotopes is going to come from the heaviest isotope because we have more of them. And so more of the mass is going to be closer to 207.9 because we have more quote-unquote pieces, or more chance of meeting that heavier isotope. Now, how we determine the atomic weight and then what is the name of the element, what we want to do is we first of all want to look at the average atomic mass. And so how we're going to deal with a problem like that is we're going to take essentially the abundance that we have, and this percentage abundance, we want to get it into decimal form. And so just as a reminder, to get a number in percentage into decimal form, divide it by 100. So we have 0.0148. And now that's in its decimal form of the percentage, and we're going to multiply that by the mass of the isotope that has that abundance. And so we'll get some number in AMUs. And we're going to do that for all 4 isotopes. So in the next table here, what I have done is I have taken the fractional abundance then, divided the percentages all by 100, and I'm going to multiply the fractional abundance by the mass of the isotope. And so these are the values I'm going to get. Now, there are 3 significant digits in this particular percentage, and so there will only be 3 significant digits in the mass, but I'm going to use all the numbers that my calculator spits out at me. And so each one of these numbers is going to have 3 significant digits in it. And then I'm going to add all 4 isotopes mass together. Now, I am not dividing by 4. Because we are doing a weighted average, not an average. So the percent abundance times the mass of the isotope, and then just add those numbers up. So the mass of the isotope is 207, and we know it to the 1's decimal place, so it'll round off to 207 AMUs. If we were to look up this mass on the periodic table, the element that is closest to this mass is lead, and it has the symbol Pb. So if we were to look at antimony here, there are 2 naturally occurring isotopes. So give us the mass of the isotopes and the abundances. Calculate the average atomic mass of antimony. Now, what we will find is that in taking our abundances, we are going to divide them by 100 to get the fractional decimal form. and multiply that abundance by the mass of the isotope. So I get 69.5175. There's going to be 4 sig figs there, and I want to make sure I'm putting units on that. And then I have 0.4250. We're going to divide that by 100. And then we have the 122.90 AMUs. And so 52.2325 AMUs. Now, in terms of sig figs, this goes to 2 numbers beyond the decimal place, so does the top one, and we're just going to add those 2 numbers together. I get 121.7500 AMUs. But can only go to the 100th decimal place, so this will round off to 121.75 AMUs. And so this is weighting then, essentially, that it is somewhere in between the mass of these 2 isotopes. It's greater than 120.9, but it's less than 122.90. All right, so you may be asked to calculate average atomic masses, okay? And in doing this, again, I am not dividing by 2, okay? We're not doing that. We are just adding the 2 numbers together with the abundance. Okay. Now, I'm going to start section 2.8, and 2.8 is pretty long, and so just, deal with this, sorry. But we're going to talk about the unit of the mole, and that's not just the pest that you find in your backyard. And so the mole was introduced by weighing by counting. So, for example, if we had to count atoms in a sample, we have to know the mass of the sample and the average atomic mass for that element. So if we were to do some similar objects, like what is the mass of 1,000 jelly beans? We know that not all the jelly beans will have the same mass. Some will have maybe, a little bit broken off from them in the manufacturing process. But we know that, let's say we sample 10 jelly beans and that we find the masses of those jelly beans. We add them up and give them an average. And we're going to divide by 10 here, because we had 10 total jelly beans, and let's say that the average mass of the bean then is 5 grams. Well, that's great now, because now 1,000 beans times 5 grams for 1 bean is going to give us our estimate. And so we have 5,000 grams. And so what we're going to find is that we can essentially count. So here it says a pile of marbles weighs 394.80 grams. 10 marbles weigh 37.6. How many marbles are in the pile? So what we can do here is we can take 394.80 grams, okay, and that has a certain number of marbles in it. And we know that 10 marbles will weigh 37.60 grams. The grams will cancel and we're going to get marbles. And so what we'll see here is that we can see that we have 105 marbles. Roughly. Now, because atoms have such small masses and we don't want to take into account those isotopes, we tend to look at that atomic mass unit, and by definition, it's 1.66 times 10 to the minus 24 grams. Now, this is on your conversion sheet, so don't do that. But we'll take that into account then, and you look at normally the average atomic mass for any element, just taking into all accounts all the isotopes that are present in nature. So for carbon, the average atomic mass is 12.011. Okay, and so because we have carbon 12, we have carbon 13, and we have carbon 14. We're going to notice the most abundant isotope is closest to the mass found on the periodic table. So carbon 12 is the most abundant isotope of carbon. Now, because we know the average atomic mass, so the average mass per atom, we can essentially count them by weighing them. So if we know the mass of 10 marbles is 39 grams, or the mass of 10 carbon atoms is 10 grams, it's not going to be, we could essentially count them. And that's what the unit of the mole is for. Now, we have 431 atoms of carbon, and we know the mass of one carbon atom on average is 12.011 AMUs. So we just need to get rid of the units of carbon. And so we have 431 carbon atoms, and we know that one carbon atom weighs 12.011 AMUs. All right, atoms of carbon will cancel, and we have AMUs. And so we will see then that if we were to weigh out 5,176, 76.7 AMUs, that would be equal to roughly 431 carbon atoms. So we have a mass and we have a number of atoms. So what is the mass in AMUs of 75 atoms of aluminum? So here we have atoms of aluminum, and one atom of aluminum on the periodic table, our periodic table, that we get for the exam, it's posted on Canvas, is 26.9815 AMUs. Okay, atoms cancel, we got AMUs, and so this number of atoms of aluminum weighs this amount. Now, how does that relate to the mole then? Well, the mole is essentially just this counting tool. It's a number, like a dozen is equal to 12, a pair is equal to 2. A mole is 6.022 times 10 to the 23rd of anything. So 1 mole of anything, and this is called Avogadro's number. This is an actual picture of Avogadro. The man has got to go and do something with that hair. But by definition, it's the mole, it's the amount of substance that contains as many elementary entities, essentially atoms, that there are in exactly 12 grams of carbon-12. So how many carbon atoms are in 2 moles of carbon? Well, if 1 mole of anything is this value, 2 moles is just twice that amount, okay? Now, what we're going to find is that this number is really, really large. It's kind of hard to fathom how big this number is. So if I were to give 1 mole of dollars out to every human on Earth, so let's say there's 7 billion people on Earth. If I were to hand out $1 at a time to all 7 billion people and then distribute 1 mole of dollars, everyone on Earth would have more than $1 trillion in the bank. And so a mole is very, very large. And so we could never count out this number of anything in lab. We could do a pair of atoms, but again, we don't have the super microscope or super tweezers to pick out 2 atoms of anything. And so we're going to use this mole to help us count a certain number, 6.022 times 10 to the 23rd atoms of, let's say, carbon. We'll be able to relate that back to mass. So counting is related to mass. So molar mass is the mass of 1 mole of anything in grams. So we could do eggs, we could do shoes, we could do marbles, okay? Or in our case, we're going to be doing atoms. So the mass of 1 mole of anything in grams. And so it will tell us that 1 carbon atom weighs 12.011 AMUs. 1 mole of carbon atoms is this number of atoms, because this is Avogadro's number, and it happens to weigh 12.011 grams of carbon, okay? So for any element on the periodic table, the atomic mass in AMUs is the mass of 1 mole in grams. So when you're looking at the periodic table, and it says 12.011, that is the mass in AMUs for 1 atom of carbon. But if you wanted to talk about this number in terms of 1 mole of carbon atoms, or 6.022 times 10 to the 23rd atoms of carbon, it would weigh 12.011 grams, which is so awesome that it actually works that way also. Let's get our pen back. 1 mole of lithium, if we were to look it up on the periodic table, will weigh 6.941 grams. Okay, and so if we count it out, which we don't want to, 6.022 times 10 to the 23rd atoms of lithium, all we have to do is go into lab and weigh out 6.941 grams of lithium from the jar, and this is how many atoms of lithium we have counted out. It's awesome. So at any periodic table, wherever it is, the atomic mass is 6.941 for one atom, and it also is the molar mass. It's this many grams, 6.941 grams for every 1 mole of that element. And so this number, the mass number on the periodic table, will tell you the mass in AMUs for 1 atom of that element, or in grams, 1 mole of that element. So what's the mass of samples of sulfur and mercury shown above if we are given them in 1 mole units? We just have to look at our periodic table. Sulfur, 32.066 grams per mole. It's the number in the box. We looked up mercury. We got to know the symbol for mercury. It's Hg, 200.59 grams per mole. And then it asks, why is there such a difference? So why do you think, even though we have the same number of atoms in each sample, there's that number of atoms of sulfur and that number of atoms of mercury, why do they weigh so differently? Well, it's because mercury has more protons and neutrons, if you think about that, our atom. So the atom's much bigger, and so therefore it's got to weigh more. So if we look at the next slide here, this is showing 1 mole of various elements. Here is sulfur, here is silicon, okay? And it will show here the molar mass from the periodic table. How much does 1 mole weigh? Now there's a link down here at the bottom of the page, how big is a mole? It's a TED Talk lesson. It's really, really good. And make sure that you go and watch that and talk about how big is a mole. Now, molecular weight. It's the sum of all the atomic weights, all the weights of the atoms in a molecule. Molar mass is the molecular weight in grams. What is 1 mole? What is the mass in grams? Now, a formula unit mass is the mass of a formula in grams. For example, NaCl, we could look up how much does sodium weigh, 1 mole of it, and how much does 1 mole of chlorine weigh, and then we could figure out the formula mass, okay? It's around 40 grams per mole. Actually, no, it's more than that, sorry. It's 22 and 35, so around 57. Now, molecular weight, something like CH4 is a molecule. Okay, and we're going to look at why they're different, but these are all non-metals bonded together. This is a metal and a non-metal. That's why we talk about formula units. But if we were to look at 1 mole of this particular compound, you just look up how much is the mass of each of the parts. So we've got carbon in here, and that weighs 12.011 grams if we have 1 mole of it. And we know we have 1 mole in the formula because the subscript there is the invisible 1. Now there are 4 moles of hydrogen. Each mole of hydrogen weighs 1.0079 grams, and we'd have to multiply that by 4 because there are 4 moles in the actual formula. And then we'd add them together. And so it's around 16 grams. And of course, we don't want to round the answer off. I'm just doing math in my head right now, but we're going to add those numbers together. Now, it says what amount in moles is represented by 0.551 grams of potassium. Now, molar mass is a conversion factor. Notice here, 1 mole of anything is a certain number of grams of weight, and we can get this from the periodic table, PT. And of course, because it's a conversion factor, we can flip it upside down. And so I'm just going to look at 0.551 grams of potassium, and I want to get that into moles. So if I look up on the periodic table how much potassium weighs, 1 mole of potassium, and I'm going to put that on there, weighs 39.0983 grams of potassium. The grams of potassium will cancel, and I will get 0.01409. And so that's how many moles of potassium we have. So there are 3 sig figs here, and there are 6 here. Now, this is a conversion factor, but it doesn't have an infinite number of significant digits because someone had to weigh this out. And so some periodic tables may only have potassium weighing 39 grams. This one has 4 numbers beyond the decimal place, so it's a little bit better in terms of periodic tables. So there are sig figs in the molar masses. So I can only have 3 in my answer, or 0.0141. Now, you do need to write moles, and you don't have to put the letter E on the end. The abbreviation is MOL, but you better tell me of what chemical, and you better tell me in this problem it was of the potassium. If you don't have potassium in your answer, it's like saying I have a dozen of something, because someone's going to say a dozen what? Just like a mole is useless without you telling me what a mole of what. I have a pair of what? Shoes? Cookies? Ooh, cookies. Puppies? So you better tell me of what chemical. Otherwise, I will write of what. Okay, especially on your homework when you're doing your ask, answer discussion stuff, or your group projects, or your homework. It needs to know of what chemical are you talking about. All right, let's look at another problem here. So we want to practice at these lovely things, and that just goes through that. What is the mass of 2.5 moles of nitrogen gas? Now, nitrogen in nature is N2. It's not just the element N. As I said before, some elements don't want to walk around by themselves. And so nitrogen in its elemental form is N2. There are actually 2 nitrogens bonded together. Okay, they're like holding hands. So 1 mole of N2, if we look up what nitrogen weighs on the periodic table, it weighs 14.066 something or other grams per mole. So this is the mass of N2, or twice that amount. So we're going to use this as a conversion factor. So I have 2.5 moles of N2. Let's get rid of the unit of mole. So 1 mole of N2 weighs 28.0134 grams. And I'm going to say of N2. You need to have these on there. If I see something like 2.50 moles times 28.0134 over 1, I'm going to go, that conversion is incorrect because 28 is not equal to 1. Even if you write moles, moles and grams here, 28 grams is not 1 mole of something. 28 grams of N2 is 1 mole of N2. This would be the correct conversion. But if you don't have the chemical on there, this is wrong. Okay, and so please put that on there. And you'll understand why when we get into more complicated problems, why you want to put the chemical formula after the grams and the moles, because we are going to be looking at chemical reactions of more than 1 chemical together, and we need to keep them straight. So if we do this problem, we're going to end up where the moles will cancel, and so our answer here should come out to be, there it is, 70.0 grams of N2. So there's 3 significant digits in the answer, and notice I have grams of what chemical? N2. All right, we're almost done here. Now, molar mass is always the mass of 1 mole. So water's molar mass, 18.0152 grams, and that's because there's 1 oxygen and 2 hydrogens. What we've done is each hydrogen weighs 1.0079 grams, and then each oxygen weighs 12.011 grams. Now, because the formula has 2 hydrogens in it, we're going to multiply that mass by 2 and then just add them all together. And so this is the mass of 1 mole of H2O, or water. So it says, how would you determine the molar mass of C2H12O6? Well, hopefully we just look it up on the periodic table and say, all right, there's 6 of the carbons, and so that's equal to 6 times what 1 mole of carbon would weigh, 12.011 grams. we have 12 hydrogens, so that'll be 12 times what 1 mole of hydrogen weighs. Oops, 9. And then 6 oxygens, or 6 times, whoops, that was weird. Whoops, let me just get rid of that. Oh, I'm close to the bottom, that's why. Or 6 times 15.9994 grams. And all you do is add them up. And so what you'll find at the very end is that the molar mass is 180.1572 grams per mole, and that is of C2H12O6. Now, we can also do the problem backwards. If we have a number of moles, we can find the mass in grams. And let's look at sodium sulfate here. So in sodium sulfate, we need to look at how much does 1 mole of sodium sulfate weigh. And so we need to look at the periodic table. And we need to deconstruct this formula to get the mass. So there are 2 sodiums, so look up the mass of sodium and multiply it by 2. There is 1 sulfur in our formula, and there are 4 oxygens. So you're going to add up all these masses to get the mass of 1 mole. So if we start out with how many moles of sodium sulfate we have, we can use the molar mass as a conversion factor. For every 1 mole of sodium sulfate, it weighs 142.0432 grams of sodium sulfate. And I got this from the periodic table. Do not round off the molar masses. Use all the numbers that the periodic table gives you. So then I come out with 0.562 grams of sodium sulfate. This has 3 significant digits. This has 7 significant digits, so my answer can only have 3. Now, we can ask in that sample then, how many moles of sodium atoms are present? Well, you might ask, how am I going to get moles of sodium from this formula? Well, just look at the formula. For every 1 mole of sodium sulfate, there are 2 moles of sodium. There's 1 mole of sulfur and 4 moles of oxygen. So we can make up a conversion factor directly from the formula of the compound. And so if we have this many moles of sodium sulfate, for every 1 mole of sodium sulfate, there are 2 moles of sodium atoms. And this is how many moles of sodium atoms we would end up with then, 3 sig figs. So if it would have asked for oxygen atoms, we would have put in here instead for 4 moles of O atoms for every 1 mole of sodium sulfate. So it's kind of cool. Now, how many moles of aspirin are in 0.360 grams of aspirin? Okay. So we can look at this question in a couple of ways, and then we've got a part A and a part B here. So let's look at part A. It's given, they've already given us the molar mass of aspirin because they didn't give us the formula of it. And so if we take our 0.360 grams of aspirin, and we know that 1 mole weighs 180 grams, we're going to put grams of aspirin in the basement, so they cancel, and now we have moles of aspirin. And so it comes out to be 0.00200 moles of aspirin. And there are 3 significant digits in that answer. Now the next question is, how many molecules of aspirin is that? Well, we've been playing around with grams and moles. That's our counting by weighing. And so we can use now the fact that we know how many moles we have. Now think back to the definition of a mole. For every 1 mole of anything, so in this case we're going to talk about aspirin, that's like counting out 6.022 times 10 to the 23rd. Now in this case, this is a molecule, of aspirin. It is more than one element put together, and so we can write molecules of aspirin, okay, for every 1 mole. And so you'll notice here's Avogadro's number. Let's get rid of the ink on here. Go back to my pen. And so we would write aspirin here. Whoops. So we have aspirin and aspirin and aspirin. And then we have aspirin. So if we were to weigh out 0.360 grams of aspirin, this is how many molecules of aspirin we actually counted out. Let's try another one. How many atoms are in the 0.551 grams of potassium? Now, whenever I see a problem like this and they have grams, I always write down the molar mass. For every 1 mole of potassium, what does it weigh? And we've already seen a problem where we've had this, so 39.0983 grams of potassium. And whenever they bring up the word atoms, I always whip out Avogadro's number, 6.022 times 10 to the 23rd. Now in this case, it will be atoms of potassium are equal by definition to 1 mole of potassium. So I'm going to write all those things out. So I have them typed out on the computer, okay? And so I'm going to start with what I'm given. So I've got my grams of potassium. Let's get rid of it. So in looking at both of these conversion factors, we're going to see that the first one, molar mass, gets rid of grams. So grams of potassium go away, and now I have moles of potassium. Now my second conversion, I can go from moles of potassium to atoms. So I can do that. So notice this is how all my conversion factors back in chapter 1.8, section 1.8, doing conversions of things is going to help me out here. And so then I end up with atoms of potassium because everything else will cancel. And I get 8.49 times 10 to the 21 atoms of potassium. All right, just 2 more slides and we're all done. What is the mass of this many number of atoms of magnesium? Now, please note, this is not in proper scientific notation, so do not blame me. I took this right out of a textbook. I'm going to write down my conversion factors. Whenever they ask about mass, I'm going to use molar mass, hopefully. Whenever they talk about atoms of something, I'm going to write down Avogadro's number. So starting with the number that I am given, I want to get rid of atoms. So I need to use this conversion factor first because it has the word atoms in it. So for every 6.022, okay, sorry, I got a typo, times 10 to the 23rd atoms of magnesium is 1 mole of magnesium. Okay, and that's Avogadro's number by definition. And you do get this number on the periodic table or on your conversion sheet. I already give it to you, so don't worry about it. If you feel like putting it onto your note card, go for it. And then every 1 mole of magnesium will get us this many grams of magnesium. And so here, if we take all our numbers and see what cancels out, we'll see that if you weigh out 85.085 grams of magnesium, that is how much this number of atoms of magnesium weighs. So effectively, if we wanted to count out this number of atoms, we would just need to weigh out this amount of magnesium. Because again, we would all be dead before we could count out this big number. So being able to just weigh out a sample and say that is equal to that number of atoms is great for us in chemistry. Last one, how many hydrogen atoms are in 72.5 grams of C3H8O? Ooh. So it has the word atoms, so let's write down Avogadro's number. Okay, it has grams of the C3H8O, so I'm probably going to have to do molar mass. Okay, so molar mass, in order to figure this out, I need to take 3 times the 12.011 for the mass of carbon on the periodic table, 8 times 1.0079 grams for the mass of hydrogen, and then 1 times the 15.9994 grams for the oxygen, and add them up. Now, I will need to use Avogadro's number. And that's the next guy here. So this is how many atoms of hydrogen are in 1 mole of hydrogen. But this one right here may not be a conversion factor that is obviously sitting in this question. But you need to know how many moles of hydrogen are in a formula of this. So in 1 mole of C3H8O, there are 3 moles of carbon, 8 moles of hydrogen, and 1 mole of oxygen. And so you need to write down this conversion factor by looking at the formula, okay? So we're going to start out with the number they've given us, 72.5 grams of C3H8O. Get rid of the grams. So let's use this first conversion factor. So grams of it, we now have moles. What I suggest is in a problem like this, if you are not in units of moles, get it into units of moles, because then everything can be converted from a unit of a mole. Now we're going to go from moles of the C3H8O into moles of H atoms. So I'm going to do that conversion next to get rid of moles. And then I have now moles of H atoms. So I'm going to use 1 mole of H atoms is this many H atoms. Okay, the number, Avogadro's number. And so these all cancel. And we get this many atoms of hydrogen are actually present in this mass of C3H8O. Now these are some of the types of problems you're going to see in mastering. I cannot tell you enough that you need to practice these. Go from atoms to grams, grams to atoms, grams to moles, moles to grams. Be able to do those types of conversions like that are found in chapter 2, because we're going to utilize and use this information in moving on to chapter 3. We will use this information for the rest of the term. And so in Chemistry 139, this is not something that you can fake. So you need to very well practice a lot at these types of problems, okay? Finding the molar mass, being able to convert using Avogadro's number. Very, very important, okay? And so remember, there are practice problems in mastering, guided inquiry for chapter 2, and then also practice problems for chapter 2. They're not worth any points, and you will not be counted off, but you can practice, practice, practice. Thank you for joining me for sections 2.7 and 2.8.